Alright, I think we'll just get started. Hello everyone. I'm Daniel Tian. I'll be your instructor today for our Assorted Combinatorics AIME lesson. So this is AIME. If you're not sure you've joined the wrong class, this is the AIME class. Today we're just going to be covering just general combinatorics. There's a lot of problems in AIME that are very hard to categorize into particular parts. There's just a lot of various things that you need to know in AIME problems. So to begin, I have a few problems that have to deal with bijection kind of stuff. There's a lot of problems in AIME where it may seem difficult, but just by changing one thing, or it turns into a completely different problem that's much easier. And I have a few examples of this. Yes, I don't think I'll be able to show the problems in the Google Meet, so I'm gonna need you guys to pull up the handout that I sent on Google Classroom. So to begin, we have problem 1. We have find the number of ordered quadruples x1, x2, x3, x4 of positive odd integers that satisfy x1 plus x2 plus x3 plus x4 is equal to 30. This is just as a bit of an introduction to bijections. So we want to find the number of positive odd integers. So x1, x2, x3, x4 are all odd, positive odd integers that is, and they sum to 30. Since they're all odd, well, we could write these like x1 is equal to, how about 2y1 plus 1, right? Every odd integer can be written in this form. And let's do that for the rest of them. And y1, y2, y3, y4 or any integers, odd or even. It can be any integer. Well, any positive integer. Well, any non-negative integer. It can be 0 as well. So, well, let's try substituting this in. We have 2y1 plus 2y2 plus 2y3 plus I'm gonna erase that. Let's look. 2y3 plus 2y4 is equal to, well, 26 if we subtract the 4 from both sides. So we have y1 plus y2 plus y3 plus y4 is equal to 13, where y1, y2, y3, and y4 are any non-negative integers. Notice, any solution to this equation gives us a solution in x1, x2, x3, x4, right? If you think about it, we only need to count the number of solutions to this equation right here. We only need to count the number of quadruples y1, y2, y3, y4 of non-negative integers that sum to 13. And that will be our answer. $13 donuts for, okay. Yeah, so this is, yeah, and then then it basically becomes stars and bars. Or this is just, well, you should be familiar with stars and bars. This is just 16 choose 3, I believe. And then just figure out what 16 choose 3 is. So yeah, so this is the idea behind bijection. We turn a rather difficult problem like finding the number of odd integers, and we change it to a different problem by finding the number of integers that satisfy this other equation instead. Problem 2 is a more complex application of this idea. For non-negative integers a and b, where a plus b is at most 6, let t of a comma b, this thing, we let this equal to 6 choose a, okay, 6 choose b, and 6 choose a plus b. Then we sum this over all possible values of a and b, and then we just want to find a sum of when t of a comma b is summed over all possible values of a and b, and then take it mod 1000. The first step here is to this is the first step. We're gonna change it to look a little like this. 6 choose 6 minus a minus b. Okay. Okay. And then I'm going to replace this with c. Okay. So I'm going to replace 6 minus a minus b with c, so that it kind of looks like this. Instead of summing over all possible values of a and b that looks like this, we're going to sum over all possible values of a, b, and c such that a plus b plus c equals 6. This is the same problem, right? Because every value of t comma a comma b corresponds to a value of this, right? In other words, we just want to find the sum of all possible values of 6 choose. We want to find the sum of all values of 6 choose a, 6 choose b, 6 choose c over all possible values of a, b, and c that sum to 6. Yeah, this already looks quite a bit nicer. Instead of having to deal with this plus thing, we have just these three things multiplied together, and that we have that a plus b plus c equals 6. Here's the real interesting part. We want to find the sum of all values of this over all. We want to sum the values of 6 choose a times 6 choose b times 6 choose c over all possible values of a plus b, a, b, and c that sum to 6. So I'm going to present to you a seemingly completely different problem. I'm going to draw 18 dots. Well, not really 18 dots, 18 objects. Right? And my question is, how many ways are there to choose 6 objects from these 18 total objects? Well, that's pretty obvious. It's 18 choose 6, right? Well, here's another way to think about it. In order to choose 6 objects from this group of 18 objects, I can choose A objects from the first column, B objects from the second column, and then the remainder from the third column, C objects from the third column. Notice if the number of ways to choose A objects from this first column is 6 choose A. The number of ways to choose B objects from this column is 6 choose B. And the number of ways to choose C objects from this column is 6 choose C. So the number of ways to choose 6 objects from these 18 total objects is also the sum of 16 choose A times 6 choose B times 6 choose C, the number of ways to choose A, B, and C, over all possible values of A, B, and C that sum to 6. I think you can see what I'm getting at here. This sum right here is equal to this sum right here. And this sum right here is equal to 18 choose 6 because they both refer to the same value. The number of ways to choose 6 objects from these 18 total objects. Thus our answer is 18 choose 6. Figure out what that is modulo 1000 and you're done. I have one other problem dealing with bijection. Misha rolls a standard fair six-sided die until she rolls 1, 2, 3 in that order on 3 consecutive rolls. The probability that she will roll the die an odd number of times is, well, you want to find the probability that she rolls the die an odd number of times. So like he can roll like 6, 3, 4, 7, 7, 2, 1, 2, 3, and then once he rolls that, she's done. And we want to figure out the probability that in total she rolls it an odd number of times. All right. First, I'm gonna make a few variables. I'm gonna let P3, that's that's a horrible P. I'm gonna let P3 be the probability that she finishes rolling in 3 dice. So probability she rolls 3 times. I'm gonna let P4 be the probability she rolls 5 times. P5 be the probability she rolls 4 times. P5 be the probability she rolls 5 times total, and so on. Then I'm gonna let O be the probability that she rolls it an odd number of times, which is obviously just P3 plus P5 plus P7 all the way to infinity. And then we have E is equal to P4. Well, she can't roll it twice or just once or just twice because that's impossible. P7, P8, and then dot, dot, dot. Immediately, we have one equation relating E and O. We have E plus O is equal to 1. That's pretty obvious. What we're gonna do, we're gonna find another equation that relates E and O. All right. Consider this. Suppose we have. So I'm gonna ask the exact same problem, but with one condition. What is the probability that Misha rolls an odd number of times, given that her first 3 rolls are not 1, 2, 3 in that order? Well, if you think about it, this probability, the probability that if you really think about it, this new question, it's kind of interesting because if we're given that her first 3 rolls are not 1, 2, 3, then we can ignore the first number, if that makes sense. And no matter what she rolls no matter what she rolls first, it doesn't really matter because it's not going to lead to a 1, 2, 3. So in this new problem that we made, we can kind of ignore the first number and just start from the second number. This is a little weird to get your mind around. But the idea is that the probability that she rolls it 4 times, so maybe she finishes like here or something in this new problem where she cannot roll 1, 2, 3 in the beginning. The probability that this happens is just P3. The probability she I guess I think I'll make a new set of variables. I'm going to let Q4 be the probability in our new problem that she rolls an odd number of times. Q5 be the probability she rolls 5 times in our new problem. Our new problem, of course, is the exact same problem, but she cannot roll 1, 2, 3 in the first 3 rolls. Q6 being the probability she finishes in 6 rolls, and so on. We have that Q4 is equal to P3, Q5 is equal to P4, and so on. Because what we can do, we can just ignore the first term. We can ignore it because the first 3 rolls are 1, 2, 3, so it doesn't matter what you get the first term. And we can just start from place 2. So it's really just the same problem, but we just ignore the first dice roll. In other words, in this problem, the probability she rolls an even number of times, I'm going to write this QE. The probability she rolls an even number of times, or Q4 plus Q6, so on. This is equal to P3 plus P5, and so on. So we have immediately that QE is equal to O. And we can do a similar thing to get that QO is equal to QO is equal to E. But there's something else. Another way you can think about it is that at the probability that she rolls say 5 times total, well, it's just 215 over 216. In other words, the probability that she does not roll 1, 2, 3 in the first 3 dice times actually, how do I explain this? It's also, we also have that QE. We can also write QE as we of course is a Q4 and so on, but we also have QO is equal to Q5 plus Q6 plus not Q6, Q7, and so on. And of course, Q3 does not exist because you cannot roll 1, 2, 3 in the first 3 dice. We have that you can kind of imagine it. It's we have Q4. We have, like, for instance how do I explain this? The probability that Q6, for instance, Q6 happens, and is the probability that that she does not roll 1, 2, 3 in the first 3 dice, and then he rolls 1, 2, 3, right? That's the probability she rolls 6 times total, right? The probability she can roll 6 times total is that she rolls 1, 2, 3 for 4th, 5th, and 6th dice, and her first 3 is not 1, 2, 3. And Q7, and kind of looks like the probability she rolls 1, 2, 3 in the 5th, 6th, and 7th dice, while not having 1, 2, 3 in the beginning, and from there it's like Q4. What I'm trying to say is we can relate like, for instance, Q7 to P4 as well. Basically Q7 kind of just looks like we don't have 1, 2, 3 in the beginning, and then we roll 4 numbers to get Q7. And the idea here is we can have another equation that relates QE and QO just by imagining that it's just the exact same problem, but removing the case that P3 happens. So it's just so we just have, like, QE is just PE, or just E, times 216 over 215, and we have QO is equal to O times 2O minus P3 times 216 over 215. Because these probabilities is just the exact same as PE and PO, but we multiply by 216 over 215 to take care of the probability, to make up for the fact that we can't roll 1, 2, 3, and we also move P3 from O. And we also have QE is equal to O, and QO is equal to E. So now we have another equation relating E and O. Sorry, it's a little long to get there. And this is the main idea. But the main idea I want you to get is that this, in order to solve this problem, you need to, you instead look at a different problem. The problem where in this case, it's the exact same problem, but you cannot roll 1, 2, 3 at the very beginning. And from here, you can get another equation relating E and O. Now we have problem 4. A token starts at 0, 0 of an XY coordinate grid and then makes a sequence of 6 moves. Each move is 1 unit, parallel to one of the coordinate axes. And then, yeah, so basically this point moves, we move randomly up, down, left, right. Then we want to find a probability that we end up like on the diagonals. So we want to find a probability we end up on these two lines. That's what absolute value of y equals absolute value of x really means. So for instance, a path like this is one possible path. Yeah, so we make 6 moves in random directions, and then we want to find the probability we land on one of these lines. I believe you can solve this recursion if you want, but there's a much cooler way to do this. Yes. I'm going to do something pretty interesting. I'm going to rotate this entire graph 45 degrees. So instead, we move in diagonal directions, and we want to land on the axes. Does this make sense? We're going to rotate this entire graph. So instead of moving up, down, left, right, we're moving diagonally, and instead of wanting to land on the diagonals, we want to land on the coordinate axes. We're going to scale everything. So instead of moving like 1 unit, like square root 2 over 2 units, we're going to move like 1 unit. 1 unit. This is going to be like the vector 1, 1. This moves 1 unit left, 1 unit down, down left, and up left. So we just did a transformation. It's the exact same problem. We just rotated everything 45 degrees. So now we're moving diagonally. Now you might be asking, why does this help at all? Here's what's interesting about this. Let's notice that we want to land on the coordinate axes, on one of these coordinate axes. So in other words, let's notice that each of these diagonals, it kind of looks like this. We choose either up or down, and we choose either left or right. Right? So each one of these diagonals can be thought of as like going up or down for each choice, and then going left or right for each choice. So basically, we make 6 choices up or down, and we make 6 choices left or right. And these determine our 6 moves. So for instance, this means up right, then up left, then down left, then up left, then down left, then down right. This should be a right arrow. It's getting a little messy. I'm going to move on to a different sheet. And since we want to land on one of the axes for at least one of these directions, these must all cancel out, right? So all we need to do is find a probability that at least one of these cancel out. All right, and this is pretty easy to figure out. In order for, like, for instance, this to cancel out, we need to have 3 ups and 3 downs. So there's 6 choose 3 ways for it to cancel out over a total possible 2 over 6 to the power of 6 ways. Same thing for this. So these are the probabilities that each one of these cancel out. So the probability that at least one of them cancels out, well, 6 choose 3, that's 6 times 4, 20 over, that's 20 over 64, which is 5 over 16, 5 over 16. This is just 1 minus the probability that neither of them cancel out. So, so answer is just 1 minus 11 over 16 squared, the probability that at least one of them cancels out. Pretty interesting question overall. Once you just rotated it, once you rotate this thing, it's pretty easy to solve. I guess the motivation for why you rotate it is because you may not want to work with diagonals. Instead, you might want to work with the axes instead. It's just something that you might want to try. Problem 5. Freddy the Frog is jumping around the coordinate plane, searching for a river, which lies on the horizontal line y equals 24. A fence is located on the horizontal line y equals 0. On each jump, Freddy randomly chooses a direction and then jumps in that direction. And once he reaches y equals 0, he cannot go beyond y equals 0 and must either go up, left, or right. And then we want to find the expected number of jumps that Freddy takes to reach the river. I hope all of you are familiar with expected value. Generally, expected value is the average number of. It's just like a fancy way to say average. We want to find the average number of jumps it will take for Freddy to reach the river. Actually, I think it'll be best if we do problem 7 first, because this is a more basic. Because problem 7 is a more basic expected value, I think. So let's just move on to problem 7. And problem 7 is just board problem 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Alright. And then we have. And then no rook is placed on the same row or column. And then the value of a square is the sum of its row number and column number. The score of an arrangement of rooks is the least value of any occupied square. And then we want to find the expected value of this score. I hope all of you are familiar with expected value. We have the expected value of an event. In this case, this event is just the score. It's just the probability that, like, for instance, we get a score of 2 times 2 plus the probability we get a score of 3 times 3 plus the probability we get a score of 4 times 4 and so on. The only possible scores here are 2, 3, 4, 5, 6, and 7. And all right. I believe this one is a bit of a casework problem. We're just gonna find each one of these probabilities and just multiply everything together. I believe this is the best way to do it. It is not that bad either. For instance, P2 is just we just have a rook here, and then we have 5 factorial, and we should have 5 factorial ways to arrange the other rooks in this place. For a problem like this where no rook can be in the same row or column, there's like n factorial ways to do it if it's an n by n square. You can figure that out by, like, putting a rook here, by going in column by column. You can go column by column. There's 5 choices for the first one, 4 choices for the second one, 3 for the third, 2 for the next, and 1 for the last. So there's 120 total cases. There's 720 total cases to arrange the rooks in any way, such that none of them are in the same row or column. So this probability is just 1 over 6. For P3, we either have a rook either here or here. If we have one that's here, if we have one that's there, there's 5 factorial ways to arrange the other rooks. And if we have one that's here, we have 5 factorial ways to arrange the other rooks. And then we have to and then we can use PIE, subtract the number of cases where they're both here, so we have to subtract 4 factorial from this total. Why is it times 2? This is the expected value. This is the probability that we get a score of 2 multiplied by 2. So yeah, the number of total cases for P3 is just 5 factorial plus 5 factorial minus 4 factorial. Oh, I hope you're all familiar with PIE. It's just the number of total cases, and then we subtract any double counts. That's really all it does. And then this is just 240. Well, we can figure out what that is later. It's 220. It's 216 over 720. We can figure out what that is later. P4, we have one in here, here, or here. And I think you can see the pattern here. We're just gonna use a lot of PIE. If we have one that's here, that's 5 factorial. If we have 3 times 5 factorial, for each one of these things. Or we could have two of them in the same arrangement. So we have minus 4 factorial, minus 4 factorial, minus 4 factorial for each pair. And then we have to add back the case that all 3 of them are there. So that's the total number of cases for this. I hope I don't need to finish this problem for you. P5 is just 4 times 5 factorial minus 6 times 4 factorial, the number of ways that 2 of them are in the same arrangement. Then we have to add back 4 times 3 factorial, then subtract 2 factorial in the case. So yeah, do that for everything. P6 for the alias. P7 actually only ends up being 1. So P7 is just this case where all 7 of them are here. And just add all of that up and that'll be your answer. Again, don't be afraid to at least start a bash. Especially sorry. Sorry about that. I just had a brief audio issue. Who? Yeah, don't be afraid to start a batch, especially in a case like this, where it's only a 6x6 board. You only have a few probabilities to figure out. And in the AIME, you have an average 12 minutes per problem, which is a very long period of time. So don't be afraid to do a bash. Of course, you shouldn't be bashing if you have to do 1,000 cases or something. But in a case like this, the number of cases is pretty small. Alright, I think I'm actually going to do this in reverse order. Let's do problem 6 next. Consider all 1,000 element subsets of the set 1, 2, 3, all the way to 2015. From each such subset, choose the least element The arithmetic mean of all of these least elements is P over Q. And then we want to, just find the expected value of the least element. I think this is a little more calculation than actual combinatorics, but I guess to begin, well, let's just figure out well, first of all, the total number of ways to choose 1,000 subsets is just 2015 and choose 1,000. The number of ways such that 1 is the least element is we choose 1 and then we choose 999 from the remaining elements. And then the number of ways to choose 2, the number of ways such that 2 is the least element is we choose 2 and then we choose 999 elements from the remaining 2013 elements. And because we cannot choose 1, and we just continue this. And this all goes all the way down to what? 2015, that's... Hope this is correct. And there's 999 choose 999 ways to have 1016 as least element. This is just what happens when you choose the largest 1000 elements. Of course, this is all taken over 2015. Of course, I've only listed number of cases, so I have to take over 2015, choose 999 to get the total number of cases. But I'm going to divide by 2015, choose 999 at the very end. So we just need to find this sum right here. This is the expected value that we're looking for. 1 times 2014 choose 999, and plus 2 times 2013 choose 999, and so on. Alright, a lot of people are saying hockey stick, and that's the right idea, but we can't immediately do that. Because, we have this pesky 1, 2, 3, 1016 at the beginning that we can't really easily fit into this. So, I'm gonna try something pretty interesting. I'm gonna write this sum like this. 2014, choose 999, 2013, choose 999, plus 2012, choose 999. Notice that I'm not using any coefficients. Why am I writing over 999? 2012, choose 999, and so on. And then to add to this, and this will go all the way to 999 over 999. And add to this, we're going to add 2013, 999, plus 2012, 999, plus 2011, 999, all the way down to 999, choose 999. And yeah, and add to this, we have not 2012, choose 999, plus 2011, choose 999. You can see what I'm doing here, right? I'm splitting this sum into a bunch of different sums. Notice that there's in total one of these. There's only one 2014 choose 999 in this entire sum. There are two 2013 choose 999s in this entire sum. There are 3 2012 choose 999s in this entire sum, and so on. So the sum of these sums is equal to this thing right here, what we're looking for. So now I'm going to find what each one of these sums are using hockey stick formula. If you're not familiar with hockey stick, it kind of looks like it should do Pascal's triangle. It takes it. You can do it from one end, and then the value that it equals to, it just kind of looks like that. So in Pascal's triangle, you go down the row. Of course, whereas each one of these values of Pascal's triangle is equal to some binomial coefficients. When this is 3 choose 2, 4 choose 2, and so on. Sum all of these together, and then this next one is your answer. This one right here is this what the sum equals to. Alright, so this right here is equal, so we have this right here, this ends up being 2015, choose 1000. This ends up being 2014, choose 1000. This ends up being 2013, choose 1000, and so on. This actually goes all the way down to 1000, choose 1000. So this sum of sums just becomes 2015, choose 1000, plus 2014, choose 1000, all the way to 1000, choose 1000. So we've reduced this massive sum of sums into something that looks like this. Now we can use hockey stick formula again, but on this. Notice that we can use hockey stick formula on this sum right here. This ends up being 2016, choose 1001. Which means that the answer that we're looking for is 2016, choose 1001, over the 2015, choose 1000, the total number of cases. Figure out what this is, and you're done. It's not really hard to figure out what this is. Just write it like 2016 factorial over 1001 factorial and stuff. We have one final problem. Freddy the Frog is jumping around a coordinate plane. This is the problem that I just gave you earlier. So, basically we start at y equals 21, and then he moves in random directions. He wants to reach y equals 24. There's also a fence right here at y equals 0. He cannot go below this fence, so if he reaches here, he has to go over left, right, or up. And we want to find the expected number of jumps it would take to reach this. I'm going to write a bunch of variables. I'm going to let, and try to stick with me here. I'm going to let E21 be the expected number of jumps it takes starting from a point at y equals 21. Notice it doesn't matter which point at y equals 21, and it'll still take the same expected number of jumps to get to the river. Of course, E21 is the expected value we are looking for. Similarly, I'm going to let E20 be the expected number of jumps it takes to get to the river, starting at a point at y equals 20. So if we start at a point like y equals 20, I'm going to let E20 be the expected number of jumps it takes to get to the river. I'm going to do this for every single point. I'm not actually going to write out everything. I'm going to let E0 be the probability that be like the expected value he gets to the river starting from the fence. So the expected number of jumps he gets, well, the expected number of jumps starting from the fence. Alright, now I'm going to relate all of these expected values. For instance, I'm going to consider E21. So suppose we start at a point at y equals E21. And once we make one jump from this point, we either stay at y equals 21, there's a 1/2 chance of that happening, or we move to, and we have a 1/4 chance of moving to y equals 22, and we have a 1 in 4 chance of reaching y equals 20, right? So you think about it, the expected number of jumps it takes to reach the river from E21 is just 1, if we take one jump, and then we add to this the expected number of times it takes to get from E22, 1/4 the probability we go to y equals 22, multiplied by the expected number of jumps it takes to get to the river starting at y equals 22. Does this make sense? Hence we're multiplying by There's a 1 in 4 chance that we make it to E22, and once we get to E22, the expected number of jumps it takes to get to the river is just, well, the expected number of jumps it takes to get to the river from y equals 22, which is E22. And we also have 1/4 times E20. If he moves down, it's 1/4 times the probability he gets to the river starting on E20. And then we have a 1.5 chance of staying at E21. So it's a 1.5 chance of staying in E21. So we multiply that by the probability, the expected number of jumps it takes to get to the river from y equals 21. Yes, we will get a huge system of equations, but it actually isn't that bad to solve, considering how most of these equations are identical. But first, let's simplify this a little. We can move this to the other side to get 1/2 E21 is equal to this thing. Let's multiply 2 by both sides, so we get E21 is equal to 2 plus 1/2 of E22 plus 1/2 E21. Well, not E21, E20. Well, let's try looking at, say, E22. Well, E22, if we take one jump from y equals 22, that's just one jump to add to our total. And then we multiply that by 1/2 chance of staying at 22, plus a 1 in 4 chance of making it to 23, and a 1/4 chance of making it to 21, going back to 21. Notice this is basically the exact same equation. We again have so we have E22 is equal to 2 plus 1/2 E23 plus E21. This is actually the case for basically every single equation. There's a few equations that we need to keep track of. First of all, E23 is a little strange because once we reach to 24, we're done. So for E23, once we take one jump, we have a 1 in 4 chance of being done. And so that's a 1 in 4 chance times 0. It's times 0 because once we're done, we don't take any more jumps. And then we have a 1 in 4 chance of going back to E22, and a 1.5 chance of staying at E23. So we have E23 is equal to, just simplifying it, this just ends up being 2 plus 1/2 times E22. Another different one is E0. This is because once we're at the fence, we cannot move down. Once we take one jump, we have a 1 in 3 chance of going to E1, and then a 2 in 3 chance of staying at E0. So here we have I believe by simplifying this, we get E0 is equal to 3 plus E1. Alright. From here, it's really just a matter of substitution. We have E1 is equal to 2 plus 1/2 E0 plus 1/2 E2. We can substitute that in here to get something that looks like 1/2 E1 is equal to 2 plus 3 over 2, that's 7 over 2, plus 1/2 E2, and this looks like E1 is equal to 7 plus E2. I believe you end up getting a pattern here. It kind of looks like 3, then 7, and then like, well, I guess we could try another one to see what it looks like. We have E2 is equal to 2 plus 1/2 E1 plus 1/2 of E3. So by substituting, we end up getting this thing, 2 plus 7 over 2 plus 1/2 E3. So we have E2 is equal to 11 plus 1/2 E3. Well, not 1/2, just E3. You can actually get a pattern here. We have E2 is 11 plus E3. E3 is 15 plus E4, or E4 is 19 plus E5, and so on. You can continue this all the way until we get up to 23, and then from there you can figure out exactly what E23 is. Once you figure out what E23 is, just go backwards to figure out what E21 is. There's a lot of problems kind of like this, where instead of figuring out the probability directly by like finding cases and stuff, you instead write each of the probabilities, or in this case, each of the expected values as variables, and then you find equations relating those variables to figure out what you want. That's all I want to go over today. Are there any questions before we finish today's meeting? All right, so I guess we'll end today's meeting here. I think this will be our my last class. So good luck. I wonder. I don't know if school has started for you, but good luck. Good luck in the future. Good luck, and hope all of you get into AIME and possibly USMO as well. Thank you.